Okay, so this is to go over the 2.1 through 2.4 review that we would have done in class after we finished all the quick checks. And I just want to go through a couple of the problems that are really kind of important for the quiz, but also want to kind of answer some of the questions that I saw on the Padlet or somewhere else. So first, what some of this chapter was about is we started to look at, instead of looking at A as a collection of vectors, which we can still do and we're still going to use, but we're starting to look at A as an entity itself, a matrix itself. So if I want to know why A is invertible, there are a multitude of theorems that we could prove through row reduction, but if we didn't want to row reduce right away, what we're going to do is we're going to take the determinant of this matrix. And this should feel familiar because it's going to be the equivalent of what we did for the cross product when we were in multivariable calculus. So the determinant of A is going to start with 1, this upper left-hand corner, and then it's going to be 1 times 4 minus 4 times negative 3, so that's minus negative 12. I'll just write that out just to make sure I'm clear. Then the next one will be 0, so minus 0, and I don't even need to write what it's going to be multiplied by. I don't really care because it's going to be 0, so I'll just leave that blank. And then minus 2 times 9, negative 3 times negative 3, minus 2. So really we're just looking for this to make sure that it says not 0. So let's just make sure of that. I've got 4 plus 12, which is 16. And then I've got 9 minus 2, which is 7, times negative 2, which is negative 14. This is non-zero. So I don't even need to know, I mean, I could have simplified it more, obviously, but really the statement is A is invertible because the determinant of A does not equal 0. Okay? And then we have some algorithms for finding the inverse of the matrix A, and I am going to go through that algorithm using a 2x2 matrix, but really the idea is that we are going to put, we are using our equation AX equals B in a new way. We're thinking about it as A times the inverse of A should equal the identity matrix. So in the same way that we row reduced an augmented matrix with A and B to get X to solve this equation, we can row reduce an augmented matrix with A and I to get A inverse. So what I'm going to set up, and I'm going to actually do this one on my calculator because I don't want to waste your time, but you should know how to row reduce by hand. But I'm going to set up an augmented matrix with A on the left side and I, the identity matrix, on the right side, 0, 1. Okay, and then I will row reduce that. And I should row reduce until the left side is the identity matrix, if it is invertible. So I'm going to go ahead and just remind us of how to put that in the calculator. Okay, you see this? All right, so I'm going to go to, feels very blurry. I'm going to hit second matrix, and I'll go over and I'll edit. Let me see if I can focus. That's better. Edit my matrix. I'm going to have a 3x6 matrix. Then I'm just going to enter all the way across. So 1, 0, negative 2, 1, 0, 0, negative 3, 1, 4, 0, 1, 0, then 2, negative 3, 4, 0, 0, 1. Okay, so now my matrix is here. I'm going to press second quit to go back to my home screen. Second matrix, go over to math, and if I scroll all the way to the bottom, I will want to go to row reduce echelon form of the matrix that I just put in A. Okay, I'm going to turn it into some fractions because I like fractions better than decimals, and there we have it. We've got the identity matrix on the left side, and then this is what used to be the identity matrix on the right side and has now been reduced to A inverse. So I'm going to go ahead and write that down here. When I row reduced, I got the identity matrix on the left side and A inverse on the right side, which ended up being 8, 3, 1, 10, 4, 1, and 7 halves, 3 halves, 1/2. So to answer my question, A inverse is that matrix we just wrote down. And we could always check that by multiplying A and an A inverse in our calculator again. Okay. And again, you can do this also by row reducing by hand. I just thought this one was a little bit big, so I did this in my calculator. Okay. Number 2, down here at the bottom, kind of asks us to do the same thing. It asks us, well, it has to deal with something with the inverse. So I've got a matrix A and a matrix B, and it wants us to find A inverse B without going through the process of doing A inverse. So I'm going to again use my equation AX equals B in this case. And I know that B could be a possible output or solution, not solution, excuse me, but a possible output for this equation because it has the same number of rows as A. A, the matrix, and the output here have to have the same number of rows to be compatible. And that means that since A is 3 by 3, X will have to be, and B, excuse me, is 3 by 2, X will be some kind of 3 by 2 matrix in order to make this work. So if I think about the equation AX equals B, and I think about how I might solve this, well, we've been given a hint in the problem that we should be able to find A inverse. That means A is invertible. So I could multiply both sides by A inverse. And on the left side, that gives me A inverse A, gives me the identity matrix. And anything times the identity matrix is itself. So what this is saying is if I use the equation AX equals B and I solve for X, that X will actually be the same as A inverse B. It will be what I am looking for without having to ever explicitly solve for A inverse. So to solve this, I'm going to again use my calculator, but I am going to set up the equation in augmented matrix with A on the left side and B on the right side. And I will put it in my calculator just like we did for this above process. And let me just show you what I get. The left side should row reduce to the identity matrix, and that's because A is invertible, which also is the same thing as one of those invertible matrix theorems. We've got a pivot in every column and a pivot in every row. And the right side row reduces to 10, 9, negative 5, negative 1, 10, negative 3. And you can pause and check that for yourself here, but that makes sense. This is the right size for what we assigned X to be over here. My final answer, A inverse B, is equal to that matrix there on the right. 10, 9, negative 5, negative 1, 10, negative 3. Okay. All right, so that's a little bit with inverses. Let's talk a little bit more about the invertible matrix theorem here. So up at the top, we've got some true-false to go over. I want to make sure that we're really thinking about our invertible matrices and about the size of our matrices and how they work. So here, and maybe this is a little bit unclear, but in the first true-false, I said that A and B are both M by N matrices. I am implying here that A and B have the same dimensions. So I probably could have worded this question a little bit more clear. Like A and B are both M by N matrices or something like that. But we want to know if A, B transpose and A transpose B are defined. Regardless of whether or not you have an instinct about this, let's just go ahead and write out what A is an M by N matrix and B is also an M by N matrix, which means that A transpose and B transpose will both be N by M matrices. Gotta close my parentheses. So when I try to put these two together, I'm getting that A times B transpose will be an M by N matrix times an N by M matrix, which is in fact defined. And then A transpose B will be an N by M matrix, and B is a M by N matrix. So these are both defined. We can multiply both of them together. So this is true. Okay, true. And now, in this situation, if A and B have the same dimensions, they're both m by n, I actually could not multiply A and B together, but I could multiply their transposes together, which is kind of nice. In B, we're asking if A times C equals A times B, and all of those, A, B, and C, are matrices, then it must be true that C equals B. For regular algebra, we might think that this is true because we could just divide by A on both sides, but we have no division in linear algebra, not with matrices. We can only multiply by a fraction that it's a scalar, or we can multiply by the inverse. So a lot of people might think this is true because you're like, okay, so you don't have division, so multiply by the inverse on both sides. But there's nothing in this problem that tells me that A is invertible. So this is false, and will only be true if A is invertible. To give a counterexample, I created the matrix A equals 1, 1, 1, 1, and B equals 1, negative 1, 1, negative 1. That way, when I multiplied A and B together, I would get the 0 matrix. 0, 0, 0, 0. Yep. Okay. Then I created C and I said, you know what? Let C be the 0 matrix itself. So AC will also equal the 0 matrix when I multiply them together, but that doesn't mean that B and C are equivalent. Okay? And again, that all comes from the fact that this is A is not invertible. In part C, we're asking if A and B are square matrices, n by n, then A times A, or this A plus B times A minus B is equal to the difference of the squares of the matrices. And here is where we have to be really careful about our basic instincts for regular algebra, because in regular algebra that would be great, that would be true, because because regular multiplication is commutative. Matrix multiplication is not commutative, so when we actually multiply this all out, I do get A squared minus AB plus BA minus B squared. And these two are not equivalent always. Wow, I can't spell equivalent. Equivalent. There we go. Not equivalent always. So this cannot always be true. Good. All right, and the last one, this one takes a little bit, I gave more space because it takes a little bit more of an argument. So we're going to let A be a 6 by 4 matrix. A is 6 by 4, and B is, sort of equals on here, 4 by 6 matrix. Then AB, when I multiply them together, it's not invertible. Now AB is a 6 by 6 matrix. It is 6 by 6. So it is square, which kind of makes me think that maybe this is false, because maybe it's a square matrix, maybe it is invertible, but we need to start with some piece of information and then try to see where that piece of information takes us. So the only information I have is about the size of these two matrices, and we don't really know, we can't say a ton about something that has more rows than columns, but we do know one fact in particular that is true about all matrices that have more columns than rows. So since B has more columns than rows, which you could also say as m is less than n, okay? B has a free variable, has at least one free variable. Because it has a free variable, I'm going to say this implies that Bx equals 0, okay, has a non-trivial. And again, the important part about non-trivial is that x does not equal 0 solution. Okay, there is something that makes this equation equal to 0 when x is not itself 0. Now, I can start branching over to my matrix AB. This implies that AB x equals 0 also has a non-trivial solution. And that happens because I know that there is something its matrix multiplication is associative. So I could multiply AB first, or I could multiply BX first. And if I multiply B times something that's not 0, I will get 0. That's what we just said in this line. So when I get 0 here, then 0 times A is also 0. That means that some x, some non-zero x, was able to be multiplied by AB and make it 0. Okay? And this is part of our invertible matrix theorem. This implies that AB is not invertible, which is exactly what we wanted. Okay. Okay, so 2 more problems here. I know I'm trying to hurry a little bit, but I do want to row reduce 4 by hand. And then 5 will be super quick. So if I want to find a matrix C whose inverse is this given, so I've been given the inverse. So there are a couple formulas you could use with a 2 by 2 matrix, including the one in the notes where I find the determinant and then I switch 2 components and make the other ones negative. I hope I'm getting this right. I'm doing this off the top of my head, but I know that the inverse of C inverse, which is C, would be 1 over the determinant of C inverse multiplied by dA negative B negative C. Okay, so I could do it that way, but I want to show you that 100% of the time you could also row reduce it like we did on the front on number 1 with the identity matrix, because whether you do C times C inverse or you do C inverse times C, they should both be equal to the identity matrix. So I am going to put C inverse on the left side, 4, 6, 5, 7, and the identity matrix on the right side. And then I will try to do this in as few row operations as we can. But I am going to multiply, I'm going to do negative 3 halves row 1 plus row 2 into row 2. So row 1 not changing, row 2 I'm getting 0, and then I'm getting negative 15 halves plus 14 halves, which is negative 1 half. And then I will get negative 3 halves and 1. Okay. Then I'm probably going to multiply row 2 times 2 into row 2. So row 1, again, not changing. Row 2, actually I should do negative 2, shouldn't I? Yeah, I'll do negative 2. So 1, then 3, then negative 2. Okay, I'm not going to divide by 4 yet. I'm going to go ahead and get rid of the 5 first. So I will do negative 5 row 2 plus row 1 into row 1. The 4 doesn't change, but the 5 does. And then I get negative 14 because I got 3 times negative 5 was negative 15 plus 1. And then I am getting negative 5 times negative 2 is 10. And then this is 0, 1, 3, negative 2. Last but not least, I just need to divide row 1 by 4. Row 1 times 1/4 into row 1. Getting 1, 0, negative 7 halves, 5 halves, and 0, 1, 3, negative 2. And there is my inverse. I have row reduced C all the way, or excuse me, C inverse to the identity matrix. So what's left over should be my inverse. And the inverse of C inverse is C. So C is equal to negative 7 halves, 3, 5 halves, negative 2. Okay, that is my inverse. And you again can check that by multiplying this matrix and the original matrix in the calculator. Actually, I'm going to show you guys how to do that without having to store the matrices, because I can do it right from the home screen. So if you press alpha zoom, it'll bring up a little screen, and yours might be different if you have a more updated calculator, but this will allow you to type in a matrix on the home screen. So I want to type in a 2 by 2 matrix, and I'm going to multiply C inverse, which is this matrix up here, and notice I'm not pressing enter though, because then your calculator will think that you're ready to calculate. So I'm just using my arrows to scroll across, and then I'm going to insert another one to multiply by C, so alpha zoom, another 2 by 2, and that's negative 7 halves, 5 halves, 3, and negative 2. When I press enter, I will get the identity matrix because a matrix times its inverse is the identity matrix. Good to go. Good check. So last, I just wanted to do one more problem that dealt with in partitioning matrices. And we're not going to actually use partitioning matrices too often, except for maybe continuing to look at matrices as a collection of vectors vertically. But this will help us practice our kind of understanding of inverses and matrix operations. So I'm just going to go ahead and multiply this out and match them up. So I know so that I could get formulas for x, y, and z. So I need at least 3 formulas here. So if I multiply the first column to the first row, I have to keep them in order, but I'm getting that ax plus b times 0 equals the identity matrix. If I multiply the first column to the second row, I'm not going to get any pertinent information, so I'm going to skip that one. And if I do the second column to the first row, I'm getting a times y plus, again, b times 0 is equal to 0. That's this entry here. Again, multiplying this second column to the second row is not super helpful, so I'll move on to the third column. Third column, a times z plus b times I will equal 0. Okay, so there are 3 equations, one for each x, y, and z. It's really helpful. Anything times 0 is going to be 0, so I've got that ax equals the identity matrix, and I'm assuming that if I have to be able to find x in terms of a, that a is an invertible matrix. So x is going to be a inverse. In this one, I've got that ay equals 0. And earlier in the true-false, we noticed that multiplying 2 matrices together could equal 0 without one of them being 0. But that was because we didn't know if a was invertible or not. Here, since we're assuming that a is invertible to get an equation for x, I can multiply by a inverse on both sides. I have to keep it on the same side. But that tells me that y is, in fact, actually equal to 0. And then finally, just a little matrix algebra here. I'm going to subtract b times I is just b, so I have negative b on this side. And then multiply by the inverse on the left side. It has to be on the left side. So I'm multiplying by, if I multiply by a inverse on the left side, I have to multiply by a inverse on the left side over here. The negative is a constant though, so I can push it to the outside, and that's fine. Okay, well, I hope this was a little bit more helpful, a little more review problems. Make sure to check out the Google Classroom for the filled notes if you need more examples, or the Quizlet that is coming up.